Okay, it is my pleasure to introduce the next plenary speaker, Professor Dan Mauldin from the University of North Texas, an old friend and co-author of Paul Erdős, and he is going to talk about Steinhaus's problem on simultaneous tilings of the plane. Dan, please.
Thank you. It is a high honor to speak in this place and to this audience. Paul Erdős was very kind and generous, and I appreciated his friendship, and he introduced me to many things in mathematics, this problem being one of them. My children are also will be very proud to know what their babysitting number is. So I'm speaking about the lattice problem of Steinhaus, simultaneous tilings of the plane. So Steinhaus in the 1950s asked, are there subsets A and S of the plane such that S meets each isometric copy of A in exactly one point? So I'll call such a set a Steinhaus set for A. Now the trivial case when A is the entire plane and S is a set of cardinality 1 is ruled out. So Sierpinski in 1958 constructed several examples, and Erdős did too in 85. And it was around this time that I heard the problem from him, and we worked on it a while, but went on to other things. I only returned to this problem later in the 90s after hearing it again from Tom Wolfe and Aleko Kekris. So in particular, Steinhaus asked, what if the set A is specified? In particular, what if A is a set of integers or the lattice points in the plane? In other words, the question really is, can S be a fundamental domain simultaneously for all rotations of Z squared? Peter Kamyath answered the question in 1992 in the case that A is a set of integers, or if A is the dense set of points in the plane with rational coordinates. But the problem remained about what about Z squared? So to get a feeling for this problem, let's check some other dimensions. There is a Borel set, which is a Steinhaus set for the integers in R1, namely the fundamental domain, the unit interval. So there is a Borel measurable Steinhaus set, but there's no Steinhaus set of any kind in R4 for Z4. And the reason is, one simple reason is that if you take Z4 and translate it by the point 1/2, 1/2, 1/2, any 2 points, one on G to the 4th and the other on this translation, are at a lattice distance apart because every integer is a sum of 4 squares. So this indicates maybe there's no Steinhaus set in the plane. However, my colleague Steve Jackson and myself showed that there is one, a Steinhaus set in the plane that meets every isometric copy of Z squared in exactly 1 point. So this is equivalent to showing that S intersects each isometric copy L. I'll use L as a lattice or copy of Z squared. But for any 2 points of S, the distance between these 2 points is not a lattice distance. In other words, a norm squared is not the sum of 2 squares. And actually, we prove something a little stronger. We construct a set S so that the distance between any 2 points squared is not even an integer. So from this point on, I'll call a set that satisfies these properties an S set. And I want to let D1, D2, D3, and so forth be the increasing sequence of lattice distances. And the important property is that the gaps in this set of lattice distances converges to 0. So the first thing is, do we have any hope that there's a definable set in the sense of being a Borel set, as there is for the line? And I want to indicate a little argument here that there cannot be a Borel set, or even a set that has the bare property. A set has the bare property means that its symmetric difference with an open set is meager. So suppose there is a Steinhaus set with a bare property. Well, first we just notice that this set S, it can't be meager, our first category, because the plane is a union of its translates by lattice points. On the other hand, its complement can't be meager, because if it were, then S would be co-meager, and S would intersect its translate by 1. But then we would have 2 points at a lattice distance apart. So since it has a bare property and it's not meager, there's a ball in which S is co-meager. So the part of the set of points in this ball that aren't in S is meager. Now it follows from this that S is essentially bounded, because if we go at a lattice distance from the center of the ball, there can't be any point on the annulus that has center that lattice distance where the ball is translated to any point on that circle. And since there's no points on that lattice and the lattice gaps go to 0, that means eventually S is the first category outside some large ball. The fourth thing about this, which is a rather involved argument, is that there's a category boundary point and a lattice L containing this point P, such that the other points of the lattice are either density points of S or density points of the complement of S. It can't be that any point other than P of L is a category density point, because if there was another point that was a category density point, we could put these 2 balls on top of each other. There would be a common point, and so those 2 points would be at a lattice distance apart. So all the points other than this boundary point P are density points of the complement. And from that, you can prove that there's a small movement of the lattice, translation of the lattice, that entirely misses our set S. So if there's going to be a Steinhaus set, we must use some form of the axiom of choice, essentially. But before I go on to talk about that, I want to talk about some results and some of the unsolved problems involving this. Is there a Lebesgue measurable Steinhaus set in the plane? If there is, of course, its Lebesgue measure is 1. Croft and Beck showed that there's no essentially bounded Lebesgue measurable set. And Kolintzakis and Wolf showed that if there is one, then it's unbounded. If there is a Lebesgue measurable set, it's unbounded. And not only is it unbounded, but the integral of over S of the modulus of x to the alpha is infinity for all alpha greater than 46/27. And this comes from the best estimates at that time in Gauss's circle problem. They also showed there's no Lebesgue measurable set for ZD for D greater than 2, and I'll return to this later. Later, Chen and I showed there's no Lebesgue measurable set for any rational lattice in RD for D greater than 2. A rational lattice is a lattice such that the inner product of any two vectors is rational. And all of these results use Fourier transform methods. Time permitting, I'll talk about that. Is there a Steinhaus set for Z3? We know there's not a Lebesgue measurable one, but there still might be one. I will give you some heuristic arguments, a heuristic argument that there is not one. Is there a Steinhaus set for rectangular lattices in the plane? And we showed, but never wrote down the proof, that for rational rectangular lattices, the answer is yes. Don't know whether such a set can be bounded. And as far as I know, not much is known about Steinhaus sets for lattices and other geometries. So the usual approach for the construction of S upon hearing the problem, of course, is to well order all the lattices into some initial type, into type C, the continuum, and carefully choose a point from each lattice so that no two points are a lattice distance apart. But this fails. And we have this was a first obstruction. There's a finite obstruction. So I have listed here 17 points. Now each of these points lies on a translate of z squared by the fractional part of each of the points. So these 17 points each lie on a different translate of z squared. No two are a lattice distance apart, but every point of z squared is at a lattice distance from one of these. So if these were the first 17 lattices, and the points you had chosen, and z squared was the 18th lattice, you're stuck. I don't know whether there's a smaller example, but as you notice, the denominators are 5 and 13, except for one, which is 65, and that came from another obstruction. So how to repair this obstruction? So we retreated and tried to be more careful. So we'll try the simplest thing we can. First, let's take an integer d and let x of d be all the lattice points with coordinates from 0 through d minus 1. And then we'll say that S is a partial S set, a D partial S set, means it meets each of the translates of z squared in exactly 1 point by these points divided by d, and that no two of them are at a norm squared distance belongs to z. So to analyze whether we can do this, for a given d and any vector in the lattice point, lattice vector v, I want to write v as y of v, which will be the remainder of, after we divide out the coordinates of v by d. So then we prove this theorem, that there's a d partial Steinhaus set if and only if there's a function L from xd to xd, this is sort of the Steinhaus lift, such that for any 2 points, x and z in xd, these two zd over whatever L does to z differs from what it does to x. That square distance isn't an integer. And moreover, if L has this property, then this image of set is a d partial Steinhaus set. Now, if you expand this star, you see that if z minus x, the norm of z minus x squared isn't in dz, then star holds. So in particular, if p is a prime and it's congruent to 3 mod 4, then we have complete freedom on what L is. Just take any function L you like, it works. So that one was easy. So now we're reduced to, can we do it when p is a prime congruent to 1 mod 4? And we'll do it when d is a power of that prime. So I want to set up the following notation. Let's take 2 points, z and x, in x sub p to the n. And we have to worry about the case where the norm squared is congruent to 0 mod p to the n. So if that's true, then if we look at their coordinates, there must be a root of -1 mod p to the n such that j sub 2 minus j sub 1 is lambda times the difference in the first coordinate. So what I'm going to do is take an element b in b to the n, and I'm going to take the line with y-intercept 0b and slope lambda. And of course we have to fold this line back into xz. And I'm going to define a function that way, and I'll call it pi sup lambda sub b of an integer I in p sub to the n. The important point about this display in the defining the function pi is the second part. And what this second part is it's the inner product of the vector in the direction of the line and where L takes the point on that line. So if we go back and put this into the equation, we find that this distance squared isn't an integer if and only if this product in the last line is not congruent to 0 mod p to the n. So one conclusion is, well, pi must be a permutation. Otherwise, we would get some congruence equal to 0. And the second thing about it is not only is each of these pi functions a permutation, but it must be a good permutation. In other words, if p to the u divides I2 minus I1, then the second factor can't be congruent to 0 mod p to the n minus u. So here's a statement of the theorem. Take a prime congruent to 1 mod 4 and look at a function mapping x of p to the n into itself. So this is a Steinhaus lift, defines a partial p to the n Steinhaus set. If and only if for each p and for each square root of -1, this displayed equation in 2 holes. Or equivalently, as I said in 3, each of the functions pi lambda b is a permutation, and it's a good permutation. So doing it for p to the n is equivalent to producing good families or permutations. Well, actually there is a good permutation of length p to the n, and it's used all the time. And this is, you just take an integer I and take its expansion in base p and reverse it. And that's a good permutation. And that's all we need. So for prime powers, it's easy to construct partial Steinhaus sets. We were able to continue this and to prove the following theorem, that for each d, there's a function L from xd into xd that defines a partial Steinhaus set no matter what d is. There's a major problem here. When you look at the prime power expansion of d, you have to put together these good permutations for different powers. And it turns out that there's another property that you need, which I won't describe. And we discovered that first property by finding the counterexample with 17 points. So you have to put these families of permutations together in a very particular way. And we also proved the following extension theorem, that if you had a function that was good for d, and d prime is divisible by d, then you could extend it. So we immediately get that if we let L sub q denote the set of rational translates of z squared, there is a partial Steinhaus set that meets every one of those, and no 2 points are at the square distance belonging to an integer. And so one problem I don't know the answer to is if it's just a partial Steinhaus set for the rational translations, must it be unbounded? But one nice thing that follows from this is that if you have a partial Steinhaus set for the rational translations, you automatically have one for the rational rotations. So if you have a partial Steinhaus set for the rational translations of z squared, then it automatically is for the rational rotations, by which I mean a rotation by a matrix that has rational entries. I should say that this fails if instead of the field of rationals, you were looking at the rationals extended by the square root of 2. You don't get this property. Okay, so this gives the next approach to the well-ordering argument. This is what we really want to do, is some kind of well-ordering argument, is we well-order all the equivalence classes of lattices. So we'll say that 2 lattices are equivalent if you can get to one from the other by rational rotations and translations. So we well-order all these equivalence classes, and we successively build partial Steinhaus sets, and so that at each step alpha, S alpha meets every lattice in L alpha, and at limit stages we just take unions. This looks good, except there's another geometric construction, obstruction, which I want to describe now. So we have a new lattice, and we want to pick a point off of that new lattice. So what could prevent us from taking a point Z1 on the new lattice? Well, it could be that there's a point we've already put into our partial Steinhaus set, C1, and that the square distance from C1 to Z1 is an integer. So we can't use that point. And for the moment, let me assume that C1 does not have rational coordinates, both coordinates rational, with respect to L. And so then there's a little lemma that if this happens, if we have a lattice and C1 does not have rational coordinates, then there's a line, it forbids a line. So there's a line, so that if you take a point in the lattice whose square distance is rational, then it must lie on that line. So we tried to pick the first point, Z1, off of this new lattice, and we couldn't do it. So that eliminates a line. Well, let's take another point on the lattice, not on that line. Well, it may be that it's at a point that there's already a point we put into the Steinhaus set, C2, so that square distance is an integer. Well, that's another line. And why can't we just continue on in this way, and eventually all the points in the lattice are eliminated? So we want to eliminate this obstruction. So let's suppose we have 3 points in C1, C2, C3 that are in our partial Steinhaus set so far, and each with square radius, and we give each a radius, a square radius that's rational. And then the thing is, we would like to say there are only finitely many lattices with points Z1, Z2, Z3 on that lattice, and that are also, each of those points are on those 3 circles. If we could do that, then, and we would then have to take our L sub alphas and close them up under this geometric construction. Now there's an exception, so we only want finitely many lattices to have points on these 3 circles. And there's an obvious exception to that, and it's a railroad track. So if you had 3 circles of exactly the same radius, and you could put a circle congruent to the triangle determined by the centers, and you could run that around. And however, that's the only exception. And this exceptional case doesn't occur anyway because no 2 points in the Steinhaus set are at a lattice distance apart. So the main thing is, this is a theorem called FourBar Linkages and coupler curves in mechanical engineering. And so what we proved was that if you have 3 distinct points in a plane and 3 positive numbers, the radii, and look at the circles determined by those. There are only finitely many triples of points in that plane where those 3 points lie on lattices. So we prove there's no more than 48. I think it's no more than 6. We had 2 proofs of this, one using Grosvenor bases, and the other one we finally got a classical geometry argument. So if we ensure that our families of lattices are sufficiently closed under this sort of operation, the lattices determined by linkages will be okay. I'll show you a little movie of what this linkage looks like. Let's not start it yet, but just, okay. Oops. Okay. So here are 2 circles. Here is, so you think, the mechanical engineers think of the circle with center Z, the origin, and the other one with center 1, 0, that's a fixed bar. And then you have 2 hinged bars corresponding to the radius of the circle. And then you have this point up here tracing out the black curve. And that point tracing out the black curve, they call it a coupler point. And what we want to show is that except in the exceptional case, only finitely many lattices are determined by such a configuration. The mechanical engineers had proven this in the generic case, but we had to prove it in all cases. Anyway, yeah, now we can play this. Yeah. So you can see what it. Yeah, that's fine. Thank you. Okay, now I go back to the talk. Let's see, to get rid of this now. Just close this one, or there we are. Okay, now I'm set. Now where is it? Okay, thank you. So now we're prepared for the well-ordering argument for the set theory. However, it's not a standard transfinite induction argument. It's rather different, and this method is very useful for closing when you need to close up something under some geometric, algebraic, or combinatorial operations. And you can really only deal with countably many things at once. So this is a way of, you prove something using a continuum hypothesis, and then you want to be able to prove it without the continuum hypothesis. So here's the way this goes, this kind of construction goes. You first build a particular enumeration of sets of equivalence classes, and I set kappas of the empty set to be the continuum. And now here's our enumeration script m sub alpha 0. And it's an increasing family of sets of equivalence classes. And each one of these families has cardinality less than the continuum. And every equivalence class is in one of these. Now we're going to inductively build a well-founded tree indexed by finite sequences of ordinals. And we're going to have 2 functions, a function kappa on this tree and a function script m on this tree. So let me just describe one more thing. So if we look at m alpha, that set of equivalence classes has cardinality less than the continuum. So we we now put on a second index which enumerates everybody that's in the equivalence classes that are in M alpha 0 into initial type. So in other words, you keep building out as long as the set of equivalence classes you have is uncountable. And when it becomes, the new ones are countable, then it becomes a terminal node in the tree. And of course, everything at a finite stage, it must become countable. And so that's the basic construction, and it has one more property, which is property 4, and that is that these equivalence classes are closed under the 4-bar linkage coupler curve construction. And then you do the transfinite induction as it takes place over the terminal nodes, or the leaf nodes of the tree, and where they have the lexicographic well ordering. And that eventually allows us to construct the Steinhaus set. So that's the end of the construction, that there exists one. Now here's an argument why there should not be a Steinhaus set in R3 for Z3. And it goes back to the very beginning. Let's just try to do one for the translates of Z cubed by rationals with a prime denominator, with denominator a prime p. So again, we build a proposed function L from xp into xp, and we want to know if that can be a Steinhaus, define its range, can define a partial Steinhaus set for p. Well, for each lambda now we're not looking at the square roots of -1. We're looking at the points lambda in xp with norm squared divisible by p. And for each b, we're doing exactly the same thing. For each b in p, we define our function pi lambda b from p into p in exactly the same way. And it turns out the following are equivalent, that this theorem, that it defines, 1 says that it defines a partial Steinhaus set, and 2 says that there's a set of points, lambda, of cardinality p plus 1, such that for each lambda and capital lambda, the square of the norm is divisible by p. And for each of those lambdas, there's a subset x sub lambda of x sub p with cardinality p squared, such that these functions pi lambda b are permutations. And that's necessary and sufficient. The problem is that there are many more permutations that have to show up here, because now we don't have just 2 roots to look at. We have p plus 1. And so for large p, perhaps 11, maybe even 5, it doesn't appear this is possible. And here's the heuristic argument. The card of x sub p is p cubed, and they're p cubed, 3 p cubed functions from xp to itself. Now the probability that a random function is a permutation is p factorial over p to the p. So we've got p squared times p plus 1 functions associated to this function L. Now if they were random and independent, which they're not, then the expected number of partial Steinhaus functions would be this n sub p, which I've displayed here. The trouble is that goes to 0 very rapidly. So it's very improbable that such a function exists. Already for p equals 11, n sub p is ridiculously small. Partial Steinhaus sets for the prime 3 have been constructed, and none have been found for p equals 5. Some SAT solvers have been worked on this problem, and they ran for a month and didn't get anything, and did not prove there wasn't one, on the other hand. Now, I'd like to talk a little bit about the measurable case. So, Kolentzakis and Wolf showed there's not a Lebesgue measurable Steinhaus set. A different argument than Beck and Croft. And in fact, their argument has been refined and generalized a bit as follows, that if lambda is a rational lattice in RD, and D is greater than 2, then there's not a Lebesgue measurable Steinhaus set, meaning that it meets every copy of lambda by an orientation preserving isometry in exactly one point. I don't know the answer if lambda is not rational. I would like to mention that this transform method fails completely in R squared. And the problem in the plane seems to involve some yet unknown aspects of planar geometric measure theory and or some insufficient estimates of convergence rates. So we're now going to think about our Steinhaus set as a function. I mean, we already have, but now we're going to look in the transform space. So the property of being a Steinhaus set for this lattice lambda, let's say lambda is the non-singular matrix A times z to the d, it just implies the following, that the sum here over all the points in the lattice is 1. And if we integrate both sides of this equation, it simply shows, just looking on the far left, that the determinant of A, the absolute value of the determinant of A is the measure of this Steinhaus set. So even if S is an almost sure measurable Steinhaus set, meaning that it does it for almost every lattice, for almost every rotation, and for almost every point x, we have that summation being equal to 1. The Lebesgue measure of S is the absolute value of the determinant of A. But there's a characterization of these measurable Steinhaus sets by Fourier transform methods. So we look at the dual lattice of our lattice lambda, or L sub A. And now here's the theorem of Kolentzakis and Wolf, that if we take a function in L1 and such that there's a constant with this sum always... Sorry, I guess I'm getting too excited. Oh.
Some things.
Let's see, it's on, isn't it? No? Is it on?
Is it okay?
Microphone, it says do something with it.
It's supposed to work.
Yeah. How is that?
Oh. Doesn't work. Maybe.
Let's see if this works. Does this work? Okay, good.
You
Yes,
stay near because-
I'll stand here.
Was it? I'm sorry. I'll remove this.
Okay.
Sorry.
Okay, let's see. Okay, so we have a function f, a functional tile, a function tile. And suppose there's this constant so that for almost every x, the sum, when you translate x by a point in the lattice and take the f value and sum them up, you always get a constant. And this is true if and only if when you look at the Fourier transform of f, the transform is 0 for every point in the dual lattice other than the origin. And furthermore, if you integrate both sides of equation 3 over a fundamental domain D, we find that this constant is the integral of f divided by the absolute value of the determinant. So here's a characterization. A measurable set has the almost sure Steinhaus property for a lattice if and only if its Lebesgue measure is the absolute value of the determinant of A and its Fourier transform vanishes on all points x so that the norm of x is a norm of some point in the lattice. So this gives us a sufficient condition under which there's no measurable almost sure Steinhaus set or Steinhaus set for this lattice. And what you do is you take a matrix M, we'll call D of M the set of square distances that occur in the lattices. And if we have if we have two matrices A and B, we say that B norm dominates A if the distance set for A is a subset of the distance set for B. And now we'll say that B strongly dominates A if the ratio of the determinants is irrational, and we'll say that it weakly dominates if the ratio of the determinants is not an integer. So here's the theorem. So take a B, a non-singular matrix B, and suppose there's some A that so that the transpose of B weakly dominates the transpose of A, then there's no measurable Steinhaus set. And the proof is just simply down here at the bottom. This sum on the left-hand side we know is constant. And we know what this constant is. But if f is a Steinhaus function for B, then it's certainly one for A. And so what we get is that the sum has to be the ratio of the determinants. But it's not an integer. So if f was a characteristic function of our partial Steinhaus set, this is impossible. So what we proved was that if you have a rational lattice, that such rational lattices, there's always such a matrix A, that B, a rational lattice determined by B, always weakly dominates some lattice A. And so there's no partial Steinhaus set. And here's a very simple example in R3 for why there's no measurable Steinhaus set for Z cubed. growth rate, another, won't have time to talk much about this. And this is, if you have a measurable Steinhaus set, a partial Steinhaus set, can you say something about how fast that set is growing as it's a partial Steinhaus set for more and more lattices? So Kolenzakis and Wolf proved the following theorem, that suppose you have a partial Steinhaus set for some sort of independent lattices, finitely many. Then the diameter of the support of such a Steinhaus set, or function, must be greater than some constant than times n raised to the 1 over d. So in particular, if d is 2 in the plane and we have a measurable partial Steinhaus set for these lattices, then it has to be growing at least that fast. Well, there's a lot more to do here, and I thank you for your attention.
Thank you very much, Dan. Maybe we have time for a very quick question or comment. Yes?
The classical concept is the fractals in the plane. They're the self-similar lattice tilings, the fractals.
I'm sorry, I can't.
Fractals.
Yes, what about
in the plane, self-similar lattice tiling of the plane.
Yes.
I have a computer algorithm which creates all fractals. Computer algorithm.
Yes.
So this is my remark about that.
Okay.
Okay. Thank you very much. Let's thank the speaker again. And the next talk is in 5 minutes.
Okay.
Technical difficulties. Something always goes wrong.
Yeah, but that's okay. I mean, it always happens.